Okay, so thank you very much. My name is Daniele Ronzani. I work as Nicola in the Research and Innovation Department of HPE. And in this presentation, that's titled Core Network KPIs towards Beyond 5G use cases and applications. We are basically going to present some features related to our commercial core network solution that actually is already adopted in some of the testbeds in this project. And we'll mostly focus on the API exposure and a little presentation of metrics availability from our 5G core, as well as including some, let's say, experimentation use cases. So just a couple of words about our 5G solution. Our solution provided by HPE is a complete software, including all the network component for managing functionalities like authentication, control signaling, quality of service management, mobility, and data traffic forwarding. And it includes all the most network functions, as you see in the pictures, that basically deploy complete end-to-end core network system. And the HPE 5G core is a standalone, fully virtualized solution, completely compliant with the 3GPP specification for the end-to-end connectivity, of course. And for that, it is adopted for many different verticals and use cases. And additionally, the 5G core also uses some different security features, which, for example, restricts malicious user terminals, if you want. In the right, you can see a list of characteristics and features. For example, you can see one of the last is the Open API for metric collection and management. That's the main topic of this presentation. Moving to, let's say, a platform point of view, that's a high-level overview of our system, consisting, of course, on the network function that I just mentioned, but also including a set of tools and feature applications that complement the platform that we provide. So the system, as you can see, provides a set of tools for example, configuration, monitoring, and alarms, and also logging aspects. Everything is allowing us to customize and dynamically, if we want, to set or check in real time also every aspect of behavior of this system. And there is also possibility to include IMS, so the IP multimedia service, in order to have a sort of combo service into that same platform. And more in the specific, in the right, I highlighted some interesting features that are basically enable the ability to perform some innovative characteristics. And if we take those, they are actually enabler for the feature like, as you can see in the title, integration, automation, and monitoring. That define, let's say, some pieces of the beyond 5G domain. Integration, particularly the possibility to make this system interacting with many different services and application using standardized API. Automation, using using the API, for example, we can make a sort of programmability of the network, also providing evolved automation of management of network functions with, let's say, a minimum involvement of human users, and some improved functionality like observability and monitoring of the network. And so with this last sentence, we also define the last feature, the monitoring. In fact, we are also provide a complete set of metrics and KPI, even reachable via APIs, or also third-party application like Prometheus, indeed we have also a built-in instance of Prometheus instance in the platform, from which we can obtain and also filter the essential metric we want. So focusing on the RESTful API, as I said, we provide a complete set of RESTful API that allow every aspect of management of core network, providing, for example, performance API, fault API, configuration API, and also provisioning. Any API is supporting the security mechanism for authentication and authorization procedures. And here in this figure, I just put some example of actions that you can perform with some of them. For example, with the provisioning API that is involving mostly the UDR network function, you can, for instance, create or delete a user equipment, a subscriber. You can also assign a profile to a specific user equipment, or you can modify the policy of them. If we look on the configuration API, you can configure all the network functions or obtain the current configuration. Or, for instance, you can also reset the configuration to the default value. For the management API, this is a very interesting set of APIs, because you can, for instance, restart a network function. So when something is not working properly, you may decide to restart the container of the network function, or you can turn on or off the network function application. So in a situation in which you have some redundancy of the network function, you need to find a way to balance the workload and the resource consumption. You can decide to disable or enable some services. Okay, so you can also programmatically create a program or an intelligent system that automatically can balance the enabler of some network function application. And finally, this is another couple of API that allow you to check the current situation of the connectivity between the AMF or the radio part. You can also reset the GNOT connection, or you can obtain some status information of some subscribers. So registration state, location, and so on. All this information, for example, can be obtained by from an intelligent entity to check the condition of the network, and automatically can decide to take some action to the core network. A very simple example is about the UDR, where that is mostly involved in the provisioning API. Here below, you can see some sections that you can modify, you can operate. Okay, so for example, you can interact with the API to modify some information like the PLMN data, or you can create or delete the provision data profile. A profile in our system is just a set of information that are associated to a specific subscriber, like slicing allowed to that subscriber, or the assigned data network name, or some policy information like maximum speed in uplink or downlink. Then you can also, of course, include, create or delete some subscriber information, or modify the actual policy profile associated to a subscriber. This figure represents an example of the actual API that you can request. Okay, so you can make this kind of request. For example, in the provision data profile, you have all the suite of the method allowed to a consumer to modify every aspect of this section. So you can create, you can get the list of the existing profiles. You can get information of the specific data profile. You can delete an existing profile, or you can create a new one. And the same with the subscribers. So you can get the complete list of the subscribers. You can get the information of an existing subscriber, delete or create a new one, or you can modify partial information of the subscriber. This in particular is one interesting API, because in this kind of with this kind of method you can modify the association to a profile. So you can modify the profile for a specific subscriber. And a particular use case, if we one way, let's say, we found to develop something that is interesting, some of the API that we provide in this case is our lab implementation of a network exposure of the network, which basically exposes certain capabilities of the core network. And in particular, with this experimental implementation, we specifically enable the replace of a slice for a user. Okay, in principle, UE, a user equipment, is firstly connected to a slice one, and then according to a certain condition or event, we want to move this subscriber to another slice. And as you can see the figure, this is our implementation of the network exposure function, and through a specific component that is able to translate standard compliant requests to specific vendor specific API, like what you see here, we can change the slice belonging of a specific user equipment, exploiting this patch method. Okay, so we can change the slice associated to a UE to another slice. And so we can also change the association of a slice, leveraging the API that we can expose. Another part is about the performance and system monitoring. As I said before, we have a suite of metrics. Okay, so we can expose some metrics starting from statistic about CPU, memory, and disk usage of the system. We can also check the performance of the controller and the user plane. Okay, so we can check also in real time the throughput, filtered also per slice, per interface, per DNN of the users, the number of PDU session active, and in which kind of slice the PDU session are active, and information about user equipment. All these information can be also retrieved via API through a set of queries that we can make to Prometheus. And this allows us also to integrate, let's say, third-party element that can take all this information and can request some action to the core network. So if we merge this API of metric collection with the API of actuating actions to the core network through the API, like, for example, provision API, we can also realize what is called a closed control loop for intelligent, if you want, for intelligent resource management. This is what we actually realize in this activity presented here. And where I leave now the floor to Nicola, if you.
Yes. Thank you very much, Daniele. So Daniele has given us a quick overview of the ways in which the 5G core is, if you want, exposed to other systems, in the sense of configurability, possibility of gathering metrics, possibility of operating from an external party on the network components, and on the users, for instance. And per se, the 5G core is a 5G technology. So in order to answer to the question, how are we going beyond 5G? Our answer is by allowing all of these interactions and enabling beyond 5G use cases. So what I'm going to show here in the next 2 or 3 slides is a little project done internally with, no, we can stay on the previous one. Thank you, Daniele. A project that we carried out with an intern recently. And the scenario is the following. So we're considering this network architecture you see on the left, in which we have 2 slices, a shared control plane, and then dedicated UPFs for each one of the slices. And we consider if you want, a business case of a third party, for instance, a service provider of some kind that buys on demand resources from the 5G network. And they want, of course, to ensure that they have enough user plane resources to serve their users, their end users on the other side, if you want, of the 5G system. But also they don't want to pay too much for these resources. So what they are facing is a scenario in which they want to be sure that their dedicated UPF1, for instance, is never overloaded. And if that is about to happen, they want to be able to leverage UPF number 2, but not too much, just enough to satisfy their global quality of service, and then to keep it off in order not to pay for it if you want. And we presume then that this external service provider has its own application function that can interoperate with a little NEF prototype and gather data through the NEF from another prototype of NW DAF function. And then to perform this load balancing, if you want, with QoS constraints based on this monitored data. So yeah, next slide, please, Daniele. So in order to carry out some tests, we took a reference traffic pattern. It's the one you see here. This is completely artificial. We just built this traffic with iPerf and with another tool to modulate the intensity of the traffic over time, and to be able to repeat it as many times as needed to carry out experiments. And we simply set a threshold, the blue line you can see there, over which we estimate that the UPF is indeed overloaded. If new users were about to come, then the required bandwidth for all users would not be guaranteed anymore. And then we estimated that beyond that threshold, the need for a second UPF is there. And with this reference traffic pattern, we have that around 18% of the time we are above the threshold. So ideally, we would need a second UPF active. Next slide, please. And to solve this problem through the data and statistics monitoring and extraction we mentioned, and through the capability of the application function to operate over the activation and deactivation of UPFs and over the shift of user PDU sessions across slices, we devised this solution. We call it a predictive approach because it is based on an algorithm, ARIMA, for those who know, that is actually analyzing traffic and making predictions of peaks of the traffic that go beyond the threshold. And when this is about to happen, the application function triggers the activation of the second UPF and the load balancing of user traffic over the 2 slices. So you can see here in the picture that the red, the red and green curves show the load of the 2 UPFs. Sometimes the green load is 0. That corresponds to when only one UPF is active, the red one in this case. And you can see that whenever the red load is about to reach the threshold, the algorithm detects this, predicts this actually, and activates the second UPF. So the green one, reaches the red, then now they are basically superposed in these time periods, because they are shifting, they are handling traffic in a 50% share, if you want. And then whenever the global throughput is then lower than the threshold again, in this case of a slightly lower threshold than the blue one, it's the yellow line, then we turn off again UPF2 and we move back all traffic to UPF1, and so on and so forth over time. You can see that with this predictive approach, we have a 0% QoS constraint violation. The global, traffic over each UPF never goes beyond the upper threshold. And because of the, let's say, conservative approach, there is a prediction, so we try to act slightly earlier than an actual threshold, an actual QoS constraint happens. Then we also have a little bit of a, we could say, resource overconsumption, and 16% of the time UPF2 is active, even if it could not be, meaning that the traffic is not really, would not be really going over the fixed threshold. We can, if we don't like this behavior, we can adopt a different approach. It's the next slide, in which we react instead of proact, right? So in this case, we don't need intelligence. We just monitor statistics about the traffic. And as soon as the application function detects that the quality of service constraint violated, so traffic goes beyond the fixed threshold in terms of load, then the second UPF is turned on. And when the total throughput goes beyond the other lower threshold that we are empirically fixing, we switch off UPF2 and we move again all traffic back to a single UPF. In this case, we slightly violate 2.8 around percent of the time the QoS constraint, because obviously we are reactive, so we are seeing something that we don't necessarily want happening, but not a lot of time, and we are saving in the, let's say, UPF2 overconsumption. In any case, this obviously is a better solution than always having two UPFs active, if what we look for is not having a double UPF always active and be paying for that. Then let me also say, we don't need to focus too much on the quantitative results. It's more about the quality of the results and the fact that these two different approaches exist and work. And then, of course, whether we can allow 2% of QoS constraint violation or not will depend on the application. We can pick between the two approaches. And then we can even tune the overconsumption of UPF2 by playing with the yellow threshold, which is, again, empirically designed, and it does not match the blue one, just to avoid a little bit of ping pong effect when traffic is very close to the threshold and goes up and down around it for some time. That really concludes our presentation. So if you have any questions, they are more than welcome.